and welcome to our webinar titled Real-Time Data Processing at Scale for the Cybersecurity Domain. Now, I guess I have to apologize for the very long title, but on the post side, we have some really interesting content prepared for you today. And now we'd like to wait a little bit for some more people to join. So we're going to fill this time by making some quick introductions. So once again, hi, my name is Stoyan Dimkov. I'm an engineer in VMware, but more importantly, I'm part of Carbon Black. And Carbon Black is one of the moving forces, the leading forces in cybersecurity nowadays. So a bit more about my background as an engineer. I've been building software for more than 12 years, and I've been working in all kinds of business domains, ranging from military software to finance, to high-frequency forex trading, to business, to software automation platforms, etc. But enough about me. I'm really happy to say that I'll be co-hosting this presentation with my fellow colleague, Ivan Markov. And he is also a senior member of our engineering team. But what's more important, he is also a big data veteran. So let me pass the word to Mike. Ivan, the stage is yours.
Yes, thank you, Stoyan. So hello, everybody. It's a pleasure to be here with all of you on this meetup. Indeed, I'm also a member of the Carbon Black crew. And as Stoyan mentioned, during quite a few years, I have been primarily dealing with data processing and analytics, but I also have my fair share in other technologies throughout the years, from desktop applications to web, to full stack applications, the whole evolution of the software industry. Yeah, I think that's all from me.
Thanks, Ivan. And now let's go to the agenda. Before we get started, I'd really like to quickly go over the topics and give you some structure of what we have ahead. We have a lot to cover, and hopefully if you're on time, we're also going to have some time for Q&A. The first thing we're going to start with is actually an engineering topic. We're going to dive into the technical problems of building a data processing platform. And that's not a coincidence. We're going to use this to set the stage for justifying and explaining why and how we came up with our own custom streaming architecture for real-time search. And once we're done there, as we're going to start from high level and diving then deeper and deeper into how we actually build this, we're going to step again back and proceed with another problem statement. Essentially, search is not everything. So we're going to talk about the need for something beyond search, about more advanced analytics. And that's where my colleague will tell you about streaming and batch architectures for analytics. And like I said, for that, we're going to leave some time for Q&A. Essentially, guys, at the bottom right of your Zoom, there should be a Q&A button. At any point of time, you can jump in and write a question, and at the end, we'll be addressing those. Or if you wish, we can jump live straight in the Q&A and ask your question. So without further ado, let's get started. So the challenges of data processing platform. Well, to be more specific, me and my team, we've been building this real-time search solution for a while now, and the original first versions used to be on-premise, and that's slowly and gradually evolved to a system in the cloud. And over the course of different designs and trial and error, we have distilled some set of problems and challenges that we faced, and some of which we keep on facing. So what I want to do right now is go over these problems and challenges categorized in three sets: in scale, elasticity, and resilience. So let's talk about scale. And we're not going to just go with a blank screen. We're going to need to first draw a very quick and high-level schematic of how Carbon Black interacts with our customers. So what we see on the left is a customer with their full network of devices. And you can think of their endpoints as laptops, desktops, and servers. And what Carbon Black does is we install a sensor software, essentially an agent on these devices, that tracks and records all kinds of activity that we then send back to the cloud. And you might ask, what kind of activity do we record? Well, essentially all kind of firewall related and significant activity. For example, opening a network port, or modifying registry entry, starting a sub-process, a DNS lookup, etc. So we push all that data to the cloud, and then we analyze it and manipulate it. We process it essentially in real time, and we build on top of it security features. Features like enabling searches and alerts. So that looks very simple, but now let's add some scale numbers to this. we have more than 7,000 customers, and that's not a big number on its own, but some of which are very big. For example, more than hundreds of thousands of devices. And this results in us having more than 6 million active devices at any point of time pushing data to us. And that means more than 1.5 billion events every minute. And this results that in our platform, we have to keep and track and store more than 20 petabytes of user data. And finally, I mentioned searches. So in our platform, each and every search could span up to 300 terabytes of index data. And our users do more than 500 search queries every minute. So enough about scale. Let's talk about elasticity. And in our case, the problems and the needs to think about elasticity all derive from data. Now, if you look at that diagram on the right, that's actual production data. And we can recognize a few unpleasant patterns. Both at the macro level of the whole stream, we have these fluctuations. And also at each individual cover, which represents a customer, we do have some moments where suddenly the traffic spikes. So essentially, we experience data skew. So we can't really anticipate the volume of traffic we're going to get from a given customer just based on the number of devices or based on what was the traffic yesterday. And also data fluctuation, a very similar term, based on external factors like when is the working time in the US, our traffic usually goes up, or on the weekends it goes down. So those fluctuations and the data skew essentially demand for us to implement load separation. And what would that mean? That would mean that we can't really tolerate a traffic spike on one customer, even to the point where we're not capable of handling that data in real time anymore. We could not tolerate that spike to affect another customer to decrease the quality of service there. And beyond load separation, also our customers demand to have the ability to have individual data retention. And that said in simple terms means that they need to be able to dictate when their data is deleted, etc. So just a simple example, one customer might want to retain their data for 30 days, but another might be willing to keep it for much longer. So beyond elasticity, we also have to quickly note the challenge about resiliency. And the subtitle really defines it very well. We're trying to build a mission-critical software in the cloud, and that's kind of a contradicting statement. In a way, cloud infrastructure can and will fail. But on the other side, we have some very specific low latency requirements for everything we do in our system. So if we can't really build a system that will never fail, what else can we do? Well, we can build a system that tolerates and anticipates unexpected failures, so it can recover. And also, if we build a system that way, it's easier to design it to tolerate and to support expected failures. So an example of expected failure is like a planned deploy, where you might destroy an old version of the service and bring up new. So at a high level, the point I'm making is, if we can't make the service never fail, we can at least design it around that to handle it better. So let's try some conclusions on those three problems I described. Well, the number one thing that comes to mind, and that's I'm usually hearing, is, but why don't you just use something like an Elasticsearch or Solar Cluster? And that does make sense. Essentially, what I've been explaining so far is just one big distributed search. Yes, but the problem is that at the scale at which we operate, we can't really deal with one big cluster of Elasticsearch. It would not fit neither on the cost or complexity perspective, because the complexity of managing, let's, for example, in our scale, that would be at least 10 or 20,000 nodes of a huge cluster, the complexity would be way beyond what we are willing to commit to. So we need something simpler to achieve the same resilience and high availability, but without the effort and complexity. So a data lake might be an answer, definitely a much more elegant and simpler approach, and also very capable of scaling well on the ingestion front. So a data lake would do that great, but sadly, data lake is not really meant to do low latency searching. So we can't really achieve that part of our requirements. So we need something in between. We need some of those ideas of big solar Elasticsearch cluster, or we need something that's like a data lake, but neither out of the box would work. And also, we kind of touched a bit on our problems with resilience and our commitment to build it in the cloud, where we can't really assume it will never fail. So we need a system that essentially kind of self-heals and reacts better to outages. And the last point, we also have to be capable of managing that system with preferably a small team. So having all those conclusions, what did we came up with? Well, we came up with our own custom internal streaming architecture, and what you see on the screen are 5 logical layers that represent it. And the concept here is that each layer does some portion of the work and is mostly decoupled from the rest. It takes some data in, it works with it, and it pushes it down the road to the next layer. So by definition there, we achieve the ability to scale each layer independently and horizontally. So in other words, we're taking one big problem and splitting it into 5 smaller problems. Now, let's review each of the layers and briefly give some context of what responsibility do we put there. So, ingestion, essentially here what we want to do is to handle the immense traffic of, for example, 6 million devices and put all data into a stream. So we start streaming to the other layers. That's the key thing here. And there in dispatch, the next layer, we start caring about the data and how to efficiently process it. So what we would do here is we would convert the data, reduce the entropy, in essence, organize the data by customer, and that would make it much easier for the other layers to achieve our goals. So now the processing layer receives a stream of organized data. And here is where is the heart of our application. We start building our distributed search. And this is also something that we break into additional stages to simplify and to scale better. So the first stage would be happening in the processing, essentially starting to build individual indexes. But then we do a couple of things. First, we gave up on streaming and we start batching batches of work, in this case, batches of indexes, to our next layer, which is the materialization. And there we essentially try to do 2 things. We will take those indexes and we try to optimize them, make them bigger, and we also persist them. And finally, in the final layer of consumption, we expose all that to the customer. So we provide APIs, we build the UI, and essentially provide the capability to execute searches, aggregate results, and essentially consume the data. All right, so let's dive a bit deeper now into ingestion and dispatch. So it all starts with the consumer device, and as mentioned, we are gathering and sending security events. So what we do here is we're batching up to 5 minutes of data on the customer side, or up to 1 megabyte of compressed data. And as you're going to see later, that's significant. So after gateways and load balancers, we end up in our ECS cluster, where a given set of services handle this. But the most important thing I want to highlight is that we have the key goal here to accept the data, authenticate it, and push it to a stream. And as already mentioned, the main goal here is throughput. So as you can see, as highlighted by these different cores, think of those cores as individual customers. We are distributing the data evenly across the stream. Right now, we are not very close to our business goal of processing each customer's data independently, but our focus here is completely different. Our goal is to ingest successfully the data. Then things dramatically change on the dispatch part of our system. At that point, now we start caring about the data. So the 2 main things we want to achieve are we need to partition it by customer, and we need to convert it into a more efficient form that's more capable of indexing. So we convert it to documents that we want to prepare for indexing, and we partition by customer. So far, great. But apart from advancing in our layers and closer to our goal, we have created a problem. And it's not immediately visible, but it was actually the biggest problem I described with elasticity. We have big data skew, and that's perfectly fine in this evenly distributed event stream. But in the next one that we are now ordering by customer, what would happen if suddenly the traffic spikes for one of our customers, let's say the orange one? Well, our choice of technology for streaming, in this case Kinesis, has some very specific limitations, and that is it has specific write capacity and read capacity for each of its shards, in this case 1 megabyte per write. And that would result in any spike would cause some very hot or very cold shards in this unevenly balanced stream. So we need some mechanisms to combat this. And what we've done is we've built our own set of services to monitor traffic and to do streamer sharding. We're going to get into more detail about this in a bit, but the key point I'm trying to make here is that now we are reducing entropy, but we are exposing ourselves to the problems of data skew. And one final note here on Kinesis, as I mentioned, we are batching up to 1 megabyte of data. That's not coincidental. We're trying to fit the data into the most efficient message size for Kinesis. And as I'm mentioning Kinesis one last time here, it's a choice of technology not with coincidence for us. It's serverless and it's very easy to reason with. In fact, we are one of the biggest users of Kinesis in AWS. So now let's talk about how we do the resharding in Kinesis. So let's start with one stream of data, and as we explained, we've already organized it in a way that customer data is close to each other. And let's see what happens in our timeline. First thing is red customer experience and traffic increase. Then our set of services responsible for managing that stream recognizes and decides to take action. So the action we can do is essentially one of two APIs, and the one we need right now is to do a shard split. And the cool thing about this is it's a very quick operation and it's not affecting anybody else on the stream. So as soon as that's complete, we now have increased the capacity for specifically the red client and effectively the red stream. How this works at a very high level, to avoid the details, well, there is a key range essentially for the messages that go to Kinesis. Based on the hash computed for each message, they would go to some of the shards. And each shard has a certain range of those keys it can accept. When we do these split and merge operations, we preserve the parent provided range of keys and we pass it to the children. So in a way, that change is not affecting at all the other shards in the stream. And now we could dive a lot into the details about how we use this, but the high level key I want to point is that this is a very easy way for us to achieve load separation. Let's quickly explore the opposites. Let's say that yellow customer experiences traffic drop. So in that case, we're over provisioning, we're paying for capacity we're not using. So the opposite action would be to execute a shard merge. And again, as soon as the operation is complete, we have achieved our goal and capacity is reduced. So the high level takeaway I'm trying to present here. So through these simple APIs and intelligently monitoring our stream, we are achieving two key goals of our architecture. We are being elastic and we are achieving load separation. Great. So let's proceed now. We have just explained how we balanced successfully our stream, but it's time to actually start building our search machine. So we have a big ECS cluster, and there we have a service that subscribes and consumes data from that organized stream. So what do we do here? We start reading the data and we start building indexes. But I haven't really said what does it mean to build an index. So let's give a bit more context. So we have built our own custom indexing and searching engine based on Lucene. And that is the core technology that powers both Elasticsearch and Soar. But given our choice to build our own clustering approach, the lower API of Lucene made a lot of sense to us. We do use some small bits of Soar core, but in a sense, the majority of our code is a custom Lucene engine. So what is important to notice here? So we've already explained how we can elastically scale our stream of data so far, and the previous layer provides this for us. But what happens here? Well, we can as well horizontally scale all the services in this layer and essentially in parallel create more indexes for each customer based on the number of shards they have. So we are very easily transferring that elasticity to the process layer. And that's great to know when we're building indexes. But as we said, we want to split that into a portion of stages. So after a certain portion of time, we're going to drop that index in S3 and give it to the next layer to deal with it. So next layer, maturization, what would it do? It would download that index that was dropped in S3 and we will start optimizing it, essentially merging indexes together to build one bigger index. And that's an optimization in two directions. We are achieving better space efficiency and better search performance to a certain degree. And for us, that certain degree is hitting 50 gigabytes or hitting 5 days. As we hit that threshold, we stop merging and two things happen. We keep on the final version again in S3, and we also keep that index hosted for search. So let's take for a moment and look at this high-level idea here. So we have separated the indexing process from the later optimization and hosting of searches. So what do we achieve here? Well, essentially, again, it's much easier to reason with the system that way and to scale independently the process layer and materialization layer. And also, we mentioned S3 as our choice where we store the data. And that's actually crucial for the whole system. S3 is both very cheap and highly available for us. Any data we write there would be written to at least 3 places. And by our design, we are confident as soon as we have the data in S3, we no longer have to worry for it. So one of my concerns in our criticism that we had about being unable or unwilling to build a huge Elasticsearch cluster, for example, would be the concern that we'd have to deal with read replicas across locations in a cluster with thousands and tens of thousands of nodes. But in our case, we don't have to. What we do here is we choose S3 to be our source of truth. And each of those services in the layers of building the indexes from the beginning to the merging to the end can be rebuilt from scratch with our data in S3. There is only one missing piece, and that is we need some kind of a service that would orchestrate all this. So what we leverage here, we have this component called index management, which would keep track of all the indexes that are being created and essentially would know which index for which specific customer and which specific portion of time is being hosted and managed by which specific container. So with those components in place, what can we do? Well, essentially, we can lose any portion of our streaming process and materialize infrastructure, and we can rebuild it straight from S3 with that extra metadata. And here is another key choice we make. For that particular part of the system, we're leveraging service architecture based on lambdas. So we don't worry about the availability of that component. We leave that to Amazon. And one final note, we'll keep on writing data on S3, so we also obviously need a mechanism to delete it. But enough about our approach to processing materialization. The key idea is this. We are splitting it to stages, we are scaling each stage independently, and we are heavily investing into relying on S3 for our availability. That simplifies a lot of things, but let's see how we can consume that data. So in the final layer of our system, we want to consume the data we've just indexed. And let's start that by exploring what the user would do. They would go to the web console and they would make a search. That would result in a hit on our APIs. And then that consumption APIs would then go to something I explained in the previous slide. We have this index management component, this orchestrating and having the information about which indexes are being hosted where. So that's essentially all we need to now trigger a heavily distributed search. So after communicating with index management, we can now initiate a search distributed across all the cores, essentially all the indexes of that given customer that are related to that specific search. So now all that is left to achieve our distributed search is to output the data and somehow process it. So we introduce 2 layers of caching, one hot and one cold. In our case, that is Redis in the form of Elasticache and S3. And from those 2 cache layers, the data gets processed by a set of services which has the key focus to do aggregation and post-processing to make the data consumable by end users. So a final write to S3 to the results, and we have delivered our data to the customer. Now, obviously, I'm oversimplifying some bits of the architecture, but the main message I'm trying to convey here is that we can build, in fact, a very, very scalable, very cost-efficient system by choosing the right cloud-first solutions and greatly simplifying our design. And also, obviously, our system does a lot more, like we do programmatic APIs or we do alerting notifications, but they are not important to the point I'm making. And with that, I can end my speech, and I hope you enjoyed the presentation about our architecture. I'll be passing now the mic to my colleague Ivan, who will explain why this is not everything we need. We need something more than just search.
Yes, indeed. I think you have to also, yes, exactly. I need the remote control. All right, so the thing is the following, the data analytics solution that we have is actually newer than the low latency search. So perhaps the easiest way to justify why we need it and why we have taken certain design decisions is to first do like a short comparison exercise. And the major difference is really we have a different set of personas, or like like stakeholders, if you wish, between the low latency search and the data analytics. Like low latency search, the main persona are the customers or like the stakeholder. This is really visible in the user interface of the Carbon Black cloud solution, and it's used by the customers. Now, the data analytics solution is primarily for subject matter experts, or as we call them, threat hunters, as well as for data scientists. And this is, by the way, defining a lot of the other things I'm going to mention. For example, we don't need such a high isolation across tenants, right? I mean, if the tenants are not really seeing the for the most part, the data in the data lake, then it's not so important. But what we really need is cross-tenant queries and analytics. Then we can have a higher latency queries, like we are not talking anymore less than 2 seconds here, we are talking minutes sometimes, but of course in exchange for more sophisticated queries. And then we need some way to run bunch workload and machine learning on the data analytics platform. And obviously, because it's internally facing, we can get by with lower SLAs. Okay. Regarding elasticity, there is a big issue with data skew with low latency search, because as we saw, the event stream of each customer has to be separated there. This is not the case for the data analytics. We don't really cluster the data by customer, as I said, at least not for now. As I said, we often, it's like a common case to have cross-customer queries in the data analytics solution. So this is the data skew is a smaller issue for us, but we have it. I'm actually going to spend some time on the next slide to describe how exactly we end up with the data skew issue and how we solve it, most importantly. We do have data fluctuation. Obviously, load separation is not an issue. And then individual data retention we have, but again, it's not on the customer level. It's because of other use cases that I'm going to clarify afterwards. Yeah, I mean, cloud infrastructure can and will fail for us as well, I guess. Robust data ingestion is therefore also a topic. Search availability during outages, apparently not so important. Again, this is for SMEs, data scientists, and lower latency search is of course out of the equation. So if I have to draw a few conclusions similar to the conclusions of Stoyan, like what are we looking for? I think it's pretty obvious, right? I mean, what we want to do is a system that can do like aggregations, roll-ups, joins, windowing, group by. Essentially, we want a big data SQL, or as they call it, traditional Hadoop data lake, or at least what is being defined as Hadoop in the cloud in 2021. Slower queries are acceptable, but okay, I mean, we should have some optimizations, like for example, ideally, the time you wait should be proportional to the traverse data, like partitioning. And yeah, I mean, we have to be capable of running batch jobs on top of the data analytics platform for computing metrics or like building feature stores and ML. By the way, I won't be touching on the ML story in this presentation. I guess there is just so much that you can say in 20 minutes, but that might be a good topic for a follow-up meetup. Now, regarding the architecture, again, we are trying to draw a parallel. So if we compare the data analytics or the data lake with the low latency search, the ingest phase is common. And it's, by the way, not to be underestimated, right? I mean, Stoyan only mentioned a few things about ingest phase, but it's really, right, the sensors get authenticated there. There is data augmentation, basically enriching of the data which comes from the sensors, and quite a few other things. So this phase we share. But then, you know, we have a different use case. So it's just not possible to reuse the same pipelines. So we have our own, as you can see below, and I'm basically gonna do a little dive into each of these things, right? One more thing which is important to mention, we are using a combination of streaming and batch, obviously, because in the end, the events get ingested in the form of or arrive at our solution in the form of like a large Kinesis stream. So we have to do streaming, but then from some point onwards, it's okay to switch to batch. So let's talk about the first phase, which is materialize and dispatch. And what you can notice on the left is that we are starting with exactly, as I mentioned, exactly the same Kinesis event stream, which is produced by the ingestion phase and which is consumed by the low latency search solution. And then how we are processing it during the streaming phases, we have Flink on Kubernetes, where the Kubernetes is the offering of AWS, like a relatively large cluster. But then if you look at this picture, like from 30,000 feet point of view, we are not doing something overly complicated, right? I mean, what we are doing is we are materializing as quickly and as efficiently as possible those events into the form of a large append-only table, right? And then during the materialization, of course, there is like a conversion from protobuf and JSON, by the way, to Avro. And then from Avro, during the materialization phase, it goes into a file system format on S3. Now, if I have to dive in a little bit into this table, it's a typical big data table. So first of all, this means it's partitioned, right? So there are like a bunch of directories, and then inside these directories, you have another set of subdirectories, which means we have like daily partitions and hourly partitioning. And then the standard data format we used for most of the tables is, of course, the Parquet format, which is like, I guess, the most widely used big data format. Now, I don't know whether I should really talk about partitioning, but just to mention, this is one of the key optimizations of big data engines. Essentially, if your SQL query happens to only query like 2-3 days, then the big data SQL engine is not even opening, so to say, the directories for the other days and not even opening the files there. I guess I have time to, even though I think this is like a common knowledge, but maybe I should also clarify what do we have besides directories there? Of course, we have files. And then the thing with those files is you really have to try on one hand to have not just one file, but many files. And then the size of those files should be ideally relatively big. Like for S3, it should be 128 megabytes or bigger. And then all of the files should be equal in size. And the reason for this, like this common knowledge in the meantime, is that the other major trick that big data engines are using to accelerate their queries is they're executing one query like in parallel, right, on multiple nodes with multiple threads. But then there is this restriction that each thread, unfortunately, can only read one file. Like one file is processed by one thread, okay? And what is happening is that if you have just one file, even if you have like 3,000 threads, I mean, it will be processed by one thread. So you don't have any parallelization. If you have way too many small files, then it's also a bit annoying because then the big data engine is lost in opening and closing and scanning directories and super small files. And then this overhead at some point becomes visible. And finally, if your files are not of equal size, what will happen is, like, imagine like a bunch of super small files and then one big. Well, your query will essentially finish when the thread processing the big file is finishing, which is also not such a great idea. So to summarize, files of equal size, not too small, not too big, 128 megabytes or bigger. And by the way, I'm describing this in detail because this is a primary thing that we have to, like primary invariant that we have to maintain, otherwise we get data skew. Now, okay, obviously the picture is not as simple as I have drawn originally. We have something called fanouts. Fanouts is basically like subset tables, if you wish. If we drill into one of those tables, what we do is essentially filtering. either vertically or horizontally. We are either just taking a subset of the rows of the original events, or we are taking a subset of the columns. And for example, just one use case to get an intuition, some of those rows, and this will be, by the way, important afterwards in the presentation, some of those rows are not just events, they could be alerts, because there is an intelligence in the sensors that we call rules. They are, by the way, quite sophisticated, and they're capable of acting on the sensor and actually detecting suspicious activity. And then we might want to isolate the alerts in a separate table simply because they have longer retention period. And then it's much easier to manage this retention period if it's in a separate table. And this way, also, if you just query alerts, because the table will be smaller, you will get faster query times. Okay, so far we were just using Flink on Kubernetes, and we were creating table-like structures, which are really just files, or I should actually really say objects on S3 with directories, or I should actually say prefixes in S3. But how do we map those to tables? Well, we use another Amazon technology. This is the Glue data catalog. For those of you who happen to have Hadoop background but don't know this, the Glue catalog, it's really just a Hive metastore under the hood. And it acts as one. It has like a AWS specific API, but also the Hive metastore API. And the registering of our tables in the data catalog is done actually quite simple. So we just have a Lambda. This Lambda is doing partition promotion, and then it's just issuing a SQL statement for each of the tables, MSCK repair table, which causes the Hive metastore, the Glue data catalog, to do its job, which is like going through each table, scanning the directories and updating its records. Of course, if we just do this, I mean, these tables would be ever growing, and at some point the cost would rise tremendously. So as I said, we have data retention policy. Here we are using, we are really taking a big advantage of S3, I must say. It's super simple. You can configure data retention policy on a bucket level, and then S3 is kind of retiring, you know, the oldest objects in your bucket per schedule automatically for you. So you don't have to do anything complicated. Data skew problem, event time versus process time. These are also well-known notions, so to say. Event time is basically when the events are created in the sensor. And process time is when Flink sees the events. And there is a whack, right? I mean, first of all, the events have to travel the internet, but then most importantly, as Jan said, those events are sometimes batched at the sensor, and they come with a delay. And there are actually even bigger reasons for this whack. I will talk about them later. But the thing is, usually process time is not interesting for the data scientists and the SMEs. They care about event time, like when the thing actually happened at the sensor. So therefore, and this is, by the way, always a topic, how you should partition. We have selected event time, which makes it much easier for our users to query and to reason, but it might result in partition files with suboptimal size, and then the queries become slow. Okay, it looks complex, but it really isn't. I have tried to explain why we have this data skew. So basically what we observed, this was really an experiment, is that, and this is heuristical and only for Carbon Black, right? A different organization might have a different distribution, but like 90% of our events arrive no later than 1 hour. It's just how it works. This is basically the status quo. And then unfortunately, 10% of those events might arrive several days later, and in the extreme cases up to 30 days. If you need an intuition, imagine that you're closing your laptop on Friday and then not working over the weekend and then opening on Monday. So what will happen on Monday is that if you had like a batch of events which wasn't sent on Friday, it will be sent on Monday. So suddenly we see events which are 3 days old. And the problem with those events which are coming late is that they're created in, unfortunately, in much smaller Parquet files. This is just how Flink works. I mean, Flink can't keep open a parquet file which is for yesterday forever, because this means that some resources or some threads would be bound to this file, even though this file will not see any significant activity during this time. So Flink is really closing the files once they become big enough, like 128 megabytes, or once a timeout happens, which is okay. I mean, this way Flink can schedule its resources better. But as a side effect, for late events, we get super very many small files, and we really have to deal with them. It's actually not difficult. We have implemented a very simple scheme. So we have these little heuristics. Okay, is the event a late arrival or not? If it's not a late arrival, we don't do anything special. We send it to Flink. Flink is saving it in a table, and that's it. Now, if the event is a late arrival, the only thing that we do is we just save it in another table, separate location, separate directory. Are we fixing the problem? No. We ended up with two tables. One looks normal, the greenish one. The reddish one is actually full of small files which are difficult to query. But, you know, it's actually very easy to implement a small utility. We call it Parquet Storage Optimizer, a small lambda. It's running from time to time. And then the only thing it's doing is it's consolidating, like it's scanning these small files, and then it's consolidating into bigger files. And then it's pushing those files into the regular table, right? And then it's of course deleting those files, or like, okay, it says 3 objects from the late landing table. And this way, okay, we might see the late arriving events even later, but we are not really having the data skew issue. A little bit about the next steps. We are already a little bit in batch mode. So those large tables that we are creating, I have only visualized 3 of them. They can be queried, and they are queried. But as I said, they are large. So if you try to query the events table for more than a day, usually you have to wait for quite a long time. And therefore, we have a set of specialized batch jobs, which are now doing something that we call the metrics table. And the metrics table are no longer just selection of subset of rows and columns. Remember, we did it already. So this is why we have the alarms and alerts table. The metrics tables are higher level notions. They use SQL aggregation, grouping, percentiles to compute something which is no longer on the event level, but which is still very, very useful to our SMEs and data scientists. And one intuition is rule hits. Like what you can do is you can build a metrics table, which is basically tracking how your rules, the intelligence that the sensor is performing. And if you see that it's not really performing very well, right? I mean, for example, it's firing way too often, like too many times per hour, then you have to take some measures. And by the way, even without going into the machine learning topic, you will see in a moment that this is a little bit closing the loop. But before that, just a few more words here. We are using Athena SQL to query all of the data, like the big tables, as well as the metrics, as well as the combination of the two, because sometimes you want to drill down. And it's performing really well, I must say. It's, of course, based on proven technology. I guess we all know this. Athena is essentially Presto in a very large deployment, serverless, and connected to the Google Catalog Hive Metastore. So far, we are happy with this. For visualization, we're using Mode and Redash. And then those interfaces, they allow you not just charting, but also writing real SQL. They're used by our SMEs and data scientists. Now, regarding closing the loop, which is, by the way, the purpose of any data analytical exercise, regardless whether this is machine learning or like a BI style analytics, is if you remember when talking about the rule hits, the idea is we are not just tracking charts, right? I mean, what we have to do is we have to improve the intelligence of the sensors. And this is exactly what our SMEs are doing in the end. By querying the data in the events, in the alarms, in the rule hits, they're drawing insights which help them to either deploy better rules or create new rules. So this is what we call closing the loops. Basically, the rules are improved, they get deployed at the sensor or in the ingestion layer. Some of them are running in the cloud. And as a result, better alarms are created or better events, right? And then we again take a look at the events and alarms. We are again evaluating the performance of our rules and our subsetting software in the sensor and improving our rules as a result. Yes, I think that's all I had to share with you. So we would gladly take any questions if you have. By the way, just to mention, if you feel more comfortable asking in Bulgarian, by all means do so. We will also answer in Bulgarian.
Yeah, both in chat and live, we can do Bulgarian and English. So we have one question in the chat. Let me see if I can answer it. So I should click answer live, I think. So Georgi is asking, is the Kinesis shard split merge comes out of the box, or is it a custom implementation? And also a follow-up, also how long does it take to split merge shards? So answering backward from the last question, the operation to split or merge takes about 10 to 20 seconds. And is it something out of the box or custom? It's actually out of the box. There is no other operation you can do than split and merge a shard in Kinesis. And also the thing I tried to very briefly explain, the fact that the parent in case of a split or the two parents in case of a merge, that you get to reuse the hash case, the hash range from the parent, that's also mandatory. So essentially the whole case I presented is the only way things happen. But it's also not the full story, because when you're putting records into Kinesis, you have two choices. You can provide a partition key, and then you would let Kinesis compute over MD5 and see where this result is distributed, so where that message would go. Or you can provide an explicit hash key, so you can explicitly say, I want this to be considered that is exactly there on that specific key. And that's simply an integer you provide. And given we said each shard has a range, starting number, ending number, essentially you're saying, I want to go right there between that range, and you're explicitly putting your message in the right shard. So to your question, is this custom or not? Well, in our case, because it's a bit more complicated, we are computing on the producer side the explicit hash key for each message we send, knowing the design we have applied. But that's not mandatory to do. You can do a simpler approach by just using a partition key based on the data you want to partition. So yeah, that's in essence the answer. Right, we got two more, I think. Let me read. Right, I'm going to answer the Kinesis one first.
I might take the private cloud question myself, right, at least for the data analytic aspects. Okay, to be honest, we are moving, like, okay, maybe I should say the question, have you considered deploying your system in a private cloud? What would be the cost difference? Actually, we are moving in the opposite direction. We are essentially migrating all of our private cloud deployments into Amazon. And we are, I think, big believers that you can do highly scalable and processing in the cloud, which is really processing huge amounts of data. It's just that you have to be careful, right? There are really two things here, in my opinion, regarding data lakes. The first thing is not everything costs the same, so you really have to take a look at your costs. And the other thing is you have to keep your options open. Because especially with Amazon and especially with their data lake offerings, there are sometimes even multiple solutions for the same problem. Like, for example, they recently introduced an Airflow instance for scheduling, DAX, which do batch workloads. But at the same time, they have, for example, the workflow functionality in the, which is of course less powerful, in the Glue catalog, like in the Glue offering. So you have to be careful here not to commit too much on a certain technology, because you might need to migrate to a different one, which is within this cloud. And then if you are not really using that much of the technology specifics, And I will give another example. Like, for example, in Glue, you have something that they call glue jobs. But if you carefully look at what a glue job is, it's just a serverless Spark cluster, nothing else. I mean, they have like a library on top of this, but I'm not sure that this library is giving you much. And besides tying you into this specific service, which is of course running in Amazon. So if you're careful, you're leaving little doors, right? You're using only open source APIs, which are well established. And then this is giving you the option to migrate to another service within the cloud. For example, you can even migrate your SQL workload from Spark to Athena, as long as you're careful how your SQL statements are arranged, right? Because you have to take account for the two dialects. Now, going back to on-prem, in theory, if you're doing those steps, you can, but the question is, should you? And I'm not really convinced at the moment anymore. I used to be kind of like a believer that on-prem is like always like somehow the cheaper solution and more control, but I'm not really sure anymore that you should. With that said, I haven't done like any sort of cost estimation, but I'm pretty sure like our fellow product managers are doing this all the time. Sorry for the long answer. I hope it was at least somewhat useful.
All right, let me take one then. So another question on Kinesis is, I'm interested, did you consider Kafka instead of Kinesis? And if yes, what made you choose Kinesis? Well, that's a long story as well, because the system I'm presenting and the choices behind it are spread around in years to go. And by the time this system was initially built and designed, the choice of using Kafka in AWS meant building and managing your own Kafka, or maybe going to Confluent or other third-party vendors. Now, we did some more recent research when MSK, which is an offering by Amazon to provide the managed Kafka, got more mature. And we found the following. In our particular use case of the way we manage elastically our streams, it would be harder to emulate the same with Kafka. In general, MSK is far less elastic and far more, let's say, more tricky to manage the way we manage our Kinesis. On the other side, we have some significant costs with our Kinesis usage, especially indirect costs in terms of VPC and networking costs. So it's a very complicated comparison, but in an essence, we need to redesign and reconsider some big portions of our system to even consider using something different for streaming than Kinesis, because our current design is very tight to the capabilities and tools that Kinesis gives you. But back to the general question of comparing Kafka on AWS and Kinesis, my quick comment is that cost is the biggest discussion here, and more specifically the indirect cost. Like if you try to build your own Kafka, you could save on the direct costs if you compare MSK with, let's say, running your EC2s and managing Kafka yourself. But apart from the operational costs of running that Kafka, you have a lot of networking costs of trying to achieve a redundant setup with high availability across AZs, because that traffic would be charged. So in essence, to conclude, yes, we have evaluated, but at this point of time, a switch to Kafka is non-trivial for us. All right, next question on the same topic. So Daniel Rankov asks, when Kinesis experienced degraded performance, did you have to handle it? How did you handle it? Great question. And Danny, nice to see you. And I assume you mean last year, Thanksgiving, that Kinesis outage. Yes, it did affect us significantly. And yes, we had to actually have a real outage that resulted in publication on our status page because we had downtimes on some of our systems. We didn't lose any data, luckily. And on the question of what did we actually do to handle it, there wasn't really much to do. In that case, that in a managed service like Kinesis, in this case, you're tied to what you can get from Amazon support and in their tools they provide. You can't really go and fix it yourself. So I can't really give you a specific answer or something we did beyond observing the state of our systems and making sure we're not losing data in the times where Kinesis was completely down.
Stoyan, shall we also answer the question of Emil Penchev? Have you considered an option like a distributed database engine, Postgres Citus data, they have a sharding engine? I'm not really sure to which portfolio this is applying. Like, is this for...
Most likely to mine, but I guess it's applicable to both.
Yeah, okay. Will you address it from your point of view and then I from the data lake point of view?
Well, let me think. I'm just reading it, so I gotta give some thought to give a reasonable answer. But the quick answer is we have considered many options, and the original evaluation about the system I'm presenting dates back to a few years ago. So I can't really tell you all the options, but I'm pretty sure we did evaluate everything that was on the table. But there is also more history that I'm really not capable of explaining in the next 5 minutes, that this product line I'm presenting is an evolution of a previous on-premise setup. So we leveraged a lot of the designs and the tools we already had. So that in essence dictates what we wanted to build. But in essence, we need an inverted search based on something like Lucene on Solar Cloud to achieve a sub-second searching. So something like a distributed database would not fit that bill on latency.
Okay, now I will try to address this question as well, but let me just say that I'm not really sure about Citus data, so I'm going to speculate here. If I remember correctly, Citus was an offering from like one of our neighbors, like a Turkish company, and they were creating like a highly distributed engine, if I'm not mistaken, which is capable of also doing query parallelization, but I might be way off. But it's not, these are details, right? Because in the end, and this might sound a bit, how to say, a bit unbalanced, but I believe those query engines which are not really based on big data technology, like how to say, like open source file formats, like Parquet, like Orc, which are not really based on Spark and Hive, because these things, they share a lot of code in between. I mean, the plane has taken off. If you have a certain data size, I don't think this is an option for you to build a data warehousing or data lake solution with, you know, good old Postgre, even if it's like in a highly distributed solution. So if this was a question regarding the data lake, no, we haven't considered this. If I'm even correct in remembering what CitusDB was, and yeah, I don't think beyond a certain data size this is really useful, because you know these tools they work together. Like the fact that Athena and Spark, for example, and Flink, they all speak the same file name format. A table in Flink, a table in Spark, a table in Athena is the same thing. It's just a Parquet file. Okay, directory. Okay, a prefix in an S3 bucket in our case, and they can exchange data this way. The fact that they can work with S3 out of the box is also very beneficial. Now, if Citus in the meantime can do this, like it's because this is the like the new generation of data warehousing, right? You're basically, your file formats are completely open. Your data lake is completely transparent. It's not like how shall I say, like Oracle DBF table spaces. This is opening a lot of opportunities, and I am not sure CitusDB is offering this. If it is, then fine, but then what's the difference between CitusDB and Athena, for example? We have already like a lot of those engines. Do we need another? I hope that helps. I'm really missing a little bit the interactive experience here.
Yeah, it would be much better in a room with people. All right, folks, any other questions? Don't be shy. All right, that's a great question. Anonymous attendee asking, great talk, do you have any open positions? Well, anonymous attendee, I must say we do. And actually, we are looking for team members in both of our teams. So I think my colleague will provide some context, like our personal emails inside VMware. So if you're interested to learn more, or you actually want to learn about what exactly do we do inside our team, you can feel free to contact us. But yeah, we do look for people.
Yes, also in the data lake, you can contact us directly on the email. And yeah, I mean, you can also find our open positions at the VMware career site.
Well, surprisingly to me, we kind of made it with time. To be honest, we actually deleted a couple of slides to be sure we're going to fit in the time, but I guess we found enough even time for Q&A, so I'm happy. One question to the audience, what do you guys think about the talk? Was it informal? Was it too much details? Was it not enough details? Did we went too high over the ideas just with like common sense, or did we give enough detail about how actually we achieved something? So any feedback right now would be useful. I guess in the Q&A or by raising hand, we can get that feedback. I actually see something like a raised hand. Let me see, how can I?
Yes, Ilyan Draganov raised hand.
Yes, how do, I think I gave him the chance to. So Ilyan, the stage is yours.
No, guys, the talk was awesome. I just wanted to thank you.
Thank
Okay,
you. Glad that you liked it.
Glad that you liked it.
Well, if that's so, I guess we can wrap it up and wish everybody a good evening. Right, Ivan?
Yes, thanks for your time, and it was a pleasure.
Thank you, guys, and see you on the next meetup.
Thanks.